52. As you can see, there's still homework out for Chapter 9. Last week was all Chapter 9, and now we're going to put Chapter 9 into action here in Chapter 10, about those electrons. So homeworks for Chapter 10 and 11 are due next week, and I encourage you, come see me, Zoom. We can talk about lecture slides. That's what we did all last week, is work through all the lecture slides. We can talk about homework problems, a lot of things we can go over. Quiz 3, that was returned. You should have grades and comments. If you're having trouble accessing that, let me know. Exam 2 should be returned back as well. And then you can see the schedule. Got another quiz, and exam 3 not far off. The review sheet should be up and ready to go for that. And then if you're considering withdrawing from the course, let me know. So these are the topics we're going to be talking about. We talked about in Chapter 9 electrons for elements or ions. Now we're going to put those together for compounds. So what's the bonding? What's happening in these compounds? And we're going to focus on one theory, Lewis theory, that describes those. If you continue in Chem 200, you'll talk about other theories that do this, but Lewis is a great, simple theory that does a great job of explaining bonding. And you can see the schedule for the next few times is here. So bonding, you can do this in a variety of ways. Now, such complicated molecules, a lot of this is done electronically, computer modeling. What does the enzyme look like? What does the protein look like? The nucleic acids. What we're going to really talk about is the basics, the ball and sticks, how they're connected together, and those same concepts apply to these much bigger, complicated systems. So this is some fundamental bonding that will apply as you continue, whether it's biology, chemistry. This is really applicable information. So let's start. The theory, as I mentioned, bonding theory that we're going to look at is focused, and I just actually read a book recently about the history of Lewis and all of his interests, but he is fascinated with electrons. So we're going to look at the bonding theory of Lewis, and then we're going to look at the shapes that these molecules take. So you can see that shape's going to be really important. What do these things look like? So 3D shape is what we're going to get to at the end, because shape, or what that looks like on the micro scale, that determines the macro scale. So shape determines properties, or structure determines properties. So that's really key, and your author, Tro, really emphasizes that in this textbook and his other textbook of structure and properties. So what does this mean practically now? Well, I have a friend in Indiana that works for Eli Lilly and synthesizes compounds for drugs. And before, you would have to make a bunch of compounds and see if they work. Now you can screen, use computers, and say, these are the likely compounds that are going to be good candidates, so make these compounds and then test those. So it's changing the field of chemistry for sure when you have these computer simulations. All right, so Lewis theory. As I mentioned, it's an introductory theory. It's a simple theory, but it can apply to so many different examples. It's a great theory, so that's why we continue to go over and use it. And it does a great job of predicting the shape, the 3D structure as well. So what we're going to see, as I already mentioned, Lewis was obsessed with electrons. So this is all about electrons. And specifically, like we talked in Chapter 9, the valence electrons. So there's a difference between valence and core. We are all about the valence electrons in this chapter, because those are the ones that are used for compounds. So it'd be great to review that Chapter 9 material, 1s2, 2s2, all of that, figuring out what the electron configuration was, and then getting to how many valence do we have. That's the application in Chapter 10. So Lewis dot structures. So what we're going to do is talk about Lewis, as I mentioned, and we're going to see dots are going to represent electrons, and I'm going to really emphasize the difference between structures and symbols. Your book doesn't really do this, but I like to emphasize that there's a difference. So I'll talk about how that relates to what we're going to do. But for sure, it's all about the valence electrons. And this Lewis dot is representing those valence electrons for atoms. Okay, so what we're going to see is a Lewis symbol now. So you can see I'm emphasizing symbols. These are just for elements. Have the element symbol. That's the core electrons. That represents all the electrons in the core, the nucleus. That's the element symbol. And then you put dots around it that represent the valence electrons. Okay, so this is the basics, the backbone of how we're going to use Lewis. So if we go back, chapter 9, 1s2, 2s2, 2p4, that's for oxygen. Okay, so if we look, remember that the energy level 1 is a core, so there's 2 electrons in core, and then we can see now there's 4 in the 2p, 2 in the 2s, so there's 6 valence electrons. So we take the symbol for the element. Remember that represents the nucleus, that represents these 2 core electrons, and then we start putting electrons around. Remember, electrons are negative, so I'm showing you how we go around. They want to be away from each other, as far away from each other as possible, and then you start to pair up. I'd probably actually even pair it up like this, so the 2 pairs are opposite of each other, but the key is there's 6 dots outside, and you can see there's 2 places for 2 on each side. So if we look at it as a square, we have a total of 2 spots per side, which can give us a total of 8 electrons. That's going to be really important to come back to this number 8. So this is the Lewis symbol for oxygen. So now I encourage you, write the Lewis symbols for the period 2 elements. Okay, so start at lithium. Think about how many valence electrons lithium has, and write the Lewis symbol, and work your way all the way to the right for neon. What's the total number of valence electrons, the symbol, and so on. You do that, you should come up with structures, symbols like this. So you can see, again, I'm emphasizing these are symbols, not structures, and we've got 1, 2 electrons opposite of each other because they're negatively charged, they want to get away. Carbon, 4, and then we have to start to pair up. We already saw oxygen here. Fluorine has 7, and then neon has 8. So these are Lewis symbols. So when you're given a problem, draw the Lewis symbol. What is the Lewis symbol? That's what it's asking for. How many valence electrons surrounded by the element symbol? So here's what governs this whole theory, okay? Lewis realized that noble gases all had 8 valence electrons. If we look at period 1, helium is an exception. It only has 2. So that stood out. And these are stable. That's why they're called noble. They don't react. They don't interact with others. So this is stability. That's what we're going for, is stability. So if everything else could get 8, then that would be stable. That would be unreactive. Okay, so this is the octet rule. And again, hydrogen and helium up top, those are the duet rules. So octet duet, that governs this theory. The octet rule, as the name implies, has to do with 8. We're talking about 8 electrons. That is what's the goal, that's the ideal. This can happen a variety of ways. It could be a transfer of electrons, or there could be sharing of electrons. Somehow these elements want to get to 8. Okay, so it depends on the situation, but these are things that can happen. And this is really good for the main group. Okay, so remember, main group is the S block and the P block. That's how we're using this to explain these bonds, these compounds, and of course hydrogen, lithium. Like I said, there's some exceptions to this octet rule. Those are the duet, that's helium, and so on. So we can go again with any element, doesn't matter where. So go ahead and pause the video and draw the Lewis symbols for phosphorus and magnesium. And remember, you're going to see patterns because phosphorus is in the same group as nitrogen. That means phosphorus has 5 valence electrons, nitrogen has 5 valence electrons. Magnesium is an alkaline earth metal, so is beryllium. You already drew beryllium with 2 electrons. Here, magnesium has 2 valence electrons. So you're going to see patterns develop. That's what you really want to do. There'll be a lot of practice in Chem 152 and Chem 152 lab of drawing these Lewis symbols, Lewis structures. So you should start to see patterns develop. Okay, so we said there's ways to get to 8. Well, we're going to talk about transferring. Okay, so when we have a metal and a nonmetal, we've already seen that that's called an ionic compound. That is characterized by a transfer of electrons. Okay, so a metal is losing the electron, and we've seen this before because metals want to go to cations, and they can transfer it to the nonmetal because nonmetals want to go to anions. Okay, so that's the sodium chloride. Now you're seeing the theory or the why behind it. Sodium goes to sodium plus to get to 8 valence electrons. Chlorine goes to chloride to get to 8 valence electrons. And those two can combine to form an ionic compound. So what draws these together is the positive charge and the negative charge. It's electrostatic attraction. It holds the ionic compound together. And this can be depicted with the theory that we're talking about. Okay, so what we're going to see here is that we can draw the Lewis symbol for sodium. Okay, that's 1 valence electron. And then we can draw the Lewis symbol for chlorine. Okay, 7 valence electrons. And then if these combine, what we just saw, the metal loses the electron, becomes Na+, the chlorine becomes chloride, gains the electron, and we notate this by putting all the electrons around it now. So that's 8. It got its 8, and then bracket it and put the charge. So now the compound is formed because this positive is attracted to this negative. The valence electron was lost. There's still electrons in there. Remember, the symbol and core electrons are still there. We're showing now chlorine has that extra electron to get to that total of 8. So the same thing can be done for any ionic compound. Potassium chloride, 1 valence electron. Chlorine, it has a spot for 1 valence electron to go in to get to 8. Put those together. Really notice here the anion, the electrons are bracketed. We have to put charges. That distinguishes that from here. No charge, no charge. Those both have charges. Okay, so it can help us even more. If we look at sodium, we already did this. 1 valence electron here. But look, sulfur's got 2 open spots. Okay, it only has 6 valence electrons. You already know the cation that forms, Na+. This might help you with determining what anion forms. Or you could look on the periodic table and see that it's 2 steps away from being an octet, so it needs to gain 2 electrons. So this is giving us an indication that this needs to happen twice. Okay, sodium needs to lose twice, and we need to fill those 2 gaps with the 2 electrons that were lost. So loss of 1 electron, loss of 2 electron, we filled 1 here, and we filled 1 here. That has a charge of -2. You see also how the sodiums are opposite of each other? Because remember, positive, positive would repel each other. They're attracted to the 2-, so they're being surrounding that. All right, so now you go ahead and do that for calcium and chlorine. Remember again, what we're doing here is the Lewis dot symbols. You can start with the element symbols, and then thinking the metals will lose electrons, the nonmetals will gain electrons. So if you take a look, 2 valence electrons. So now calcium is going to lose 2 electrons, but if you take a look, there's only 1 spot available. Okay, so it might help to think about the ions that form. Calcium becomes 2+, and if we lose 1 of those electrons, it goes here. And if we lose another one of those electrons, it goes here. So that helps us, this is the theory that helps us come up with this idea why calcium chloride forms that compound, CaCl2. So this is how Lewis symbols can help with ionic compounds. So it's transfer of electrons. The majority of our time, though, is going to be about sharing electrons. Okay, so that takes us to Lewis structures. That's different than Lewis symbols. And this is about nonmetals. When nonmetals bond, they share electrons. Okay, that's the way they achieve an octet. There's no transfer, there's no positives, there's no negatives. They're sharing to achieve an octet. We will talk later about, some people's definition of sharing is a little bit different, so that can happen in here with compounds as well. Atoms can share unevenly or evenly, so we'll look at that. Electrons appear in the space between atoms, so that means both atoms are being surrounded by that electron, so both are getting that counted towards their octet, or being satisfied, if you will. So if we take a look, Lewis symbol, hydrogen and oxygen. So this is different. We're not going to be taking this and putting this over here. Remember, it's not a transfer, a positive, negative. They're going to surround each other. Okay, so let's take a look. I'm circling here 8 electrons that are around oxygen. So oxygen has an octet. Well, if you also take a look, hydrogen is being surrounded by 2 electrons. And remember, it only needs a duet. This hydrogen is being surrounded by 2 electrons. So it needs a duet, and it's satisfied. So everyone here is sharing, surrounded by the electrons that they need. This is a good Lewis structure for water. And that's shown a little bit more clearly here. You can see the duet, octet, and duet that are being satisfied. So this is what we're going to be doing, drawing Lewis structures and accounting for atoms that are in the center, that are bonded to outside atoms, and then we're going to disperse electrons. So everyone, it also helps to talk about them like people. We want to treat everyone to get what they want. We want them to be happy. Maybe that helps you, maybe it doesn't. But this is what we're going for to get these rules satisfied, to have good Lewis structures. All right, so what we just saw with water then is our dots, but I want to highlight a few things. So if dots are between atoms, that's a bonding pair. Okay, that's representing 2 electrons. 2 electrons make 1 bond, so you might see it as dots or a line representing 2 electrons. Okay, and especially if I'm writing like this or even on the board, I would even represent the lone pairs. You can see here, the lone pairs are not a bond, they're just on oxygen. You can represent with those with 2 dots or a bar as well. So that's 2, 4, 6, 8 electrons. So we call these lone pairs or non-bonding electrons. And these are bonds or bonding pairs of electrons. So then it's really important to be able to identify how many total electrons are there, how many bonding electrons, how many lone pair electrons, all of these things that we'll come back to. So again, mentioned you can use lines however you see fit to draw this in, but you want to make sure your drawings are very clear. Sometimes people will just have random dots. Is that an electron? Is that an accident? What's going on there? So make sure you're very clear on what you're drawing. All right, so we're starting out with simple covalent bonds. Okay, so these are the diatomic molecules. So this is the ones you've looked at before, hydrogen, nitrogen, oxygen, and then the halogens. But what we're going to see is this Lewis theory really helps explain why these are diatomics. Okay, so hydrogen needs 2 electrons, and it has 1. Well, you can imagine then, if it's right next to another, life looks pretty good for both of them if they come together and share. Okay, so I took kind of like a puzzle piece here and put a puzzle piece here, and I want to caution you at doing this. This isn't necessarily the best approach, but I am just showing you this at this point to see how they're sharing. Same can be done for chlorine. You can see chlorine needs to have another electron to be surrounded by 8. So the same thing can happen to chlorine. And that's where we get to our structures of the diatomic molecules. So 1 bond, 2 electrons here. And we've got a single bond here, that's 2 electrons. And then each has 6 lone pairs. Okay, so the chlorines have an octet here and here, and the hydrogens have a duet. This helps explain why H2 exists. This helps explain why Cl2 exists. So that's the structures for those molecules. We're going to add to this. We'll have other types of bonds. So might need to share more than 1 pair of an electron. So a double bond, that's 4 electrons. Triple bond, that's 6 electrons. So really want to caution you, sometimes when students first start drawing Lewis structures, it just double, triple bonds show up everywhere, okay? Please note, this should be a last resort, okay? What we're saying is, when we draw a Lewis structure, okay, so carbon dioxide's Lewis structure looks like this. And what I'm saying is, with this double bond here and this double bond here, we don't have enough electrons to go around. We really have to share. If you've ever had to share a car or clothes or toys, whatever you've had to share in life, you know that's not preferable. You don't want to share if you can have your own stuff, right? Wouldn't that be nice? So what we're going to see though later is that we can't draw a molecule of carbon dioxide without sharing. Okay, so if we drew them all single bonds, there's too many electrons here. Okay, so they don't have enough electrons to go around, just like you don't have enough toys to go around. So we get rid of this one, we get rid of this one, we get rid of these, and because we're so short, we have to share a double bond here and a double bond here. Now that's the good Lewis structure for carbon dioxide. So share only as a last resort. All right, so oxygen looks a little different. Okay, you can see there's 2 spots available here because only 6 valence electrons. So what happens then is if 1 bond forms, you can see neither have an octet. It's still not satisfied. Okay, so we have to go to a higher bond order. We need more bonds being shared. And remember, bonds are between the atoms. So what we're going to do is add another bond here. So that looks like this diatomic oxygen with a double bond and 2 lone pairs. Now you can count them: 2, 4, 6, 8 electrons around this oxygen and the sames around this oxygen. And now you can see them here a little bit better. So triple bond, we go up even more. Nitrogen. Okay, if you stop with a single bond, we don't have octets. If you went to a double bond, you still don't have octets. So it takes a triple bond here and now a lone pair on each nitrogen to get to the octet. So you can see I'm drawing these the same, really. Okay, we had oxygen, we had nitrogen, triple bond, oxygen, double bond, then we had chlorine, single bond. So I'm drawing them and they look kind of the same, right? I mean, of course there's more lines there, but what I want to point out is these bonds are different. Okay, what I mean by that is I mean in terms of stability and distance. Okay, so a single bond has a longer distance. It's much farther away than a triple bond, which is really short. And the stability, the triple bond is shorter and stronger. The single bond is longer and weaker. So that's the basics of drawing Lewis structures. Okay, so now we're going to go for it. Okay, so here's your steps for drawing Lewis structures. And remember how we were looking at the Lewis symbols to start? So that can help you practice on that. But what you need is the total valence electrons. Okay, and we'll do ions. So if it's a cation, then remember a plus means a loss of electron, an anion negative means a gain of electron. So you need to come up with the total number of electrons. And I always say take these electrons and then put them in one pot. So I mentioned earlier Lewis symbols sometimes can look like Lego pieces or puzzle pieces. Let's put the puzzle piece next to the other puzzle piece. Don't worry about that. Just put all the electrons in one pot. So you count them up and you get 20 electrons or 30 electrons, whatever it is. Second thing you need to do is you need a central atom. Okay, so that will be the lower group number. And actually, we'll talk about this later in the chapter. The best way to look at it in terms of electronegativity. So think about that later when we get to electronegativity. If it has low electronegativity, it should be the central atom. Remember, hydrogen can only form one bond, so hydrogen will never be a central atom. It's always a terminal atom or one on the outside. Attach single bonds. Okay, so you got a central atom, you got atoms surrounding it, so make single bonds connecting those. And then fill the octet of the outer atoms. Okay, remember everyone's going for octets except for hydrogen. So go for octets for the outside. And then count your number of electrons. Does it match up? Okay, maybe you have extra. So put the remaining electrons on the central atom. Maybe you don't have enough. Remember, saw with carbon dioxide, so you need a double bond, or with nitrogen, you needed a triple bond. So you got to share some more. That's what you do if you don't have enough electrons to go around. If you even have more electrons, there's some exceptions to this octet rule. You can see here this is called an expanded octet. We'll talk about a few examples of that, and that happens on period 3 or lower. So I encourage you to stop now and do those steps for these examples. Okay, so go for it, and then I'll talk about a few. All right, so what I want to talk about is going through the steps. Okay, first step here, we'll do NF3 is count the total number of electrons. So nitrogen has 5 valence electrons. Fluorine has 7 valence electrons, and there's 3 of those fluorines. So that has a total of 26 valence electrons. Okay. So then we need to determine our central atom. If we look, fluorines to the far right on period 2 in comparison to nitrogen, and that's indicating that it does not want to share electrons. Okay, we'll see electronegativity that'll help us with that. So that means nitrogen is our central atom, and we've got our fluorines surrounding it. And remember, our steps are to connect single bonds to those fluorines. Okay, so right there, that takes up 6 electrons. 2, 4, 6 for each bond, so we're down to 20. So now, remember octets around the outside atoms. So I'm putting octets, and you can see here, that's going to lead me to 8 electrons around each fluorine. Okay, so great, fluorines are happy, they've got octet, and then if we go 8 times 1, 2, 3 fluorines, that's 24 electrons. We still have 2 left. So I put 2 here. Remember, any extra electrons go on the central atom. And now look at this. Nitrogen surrounded by 2, 4, 6, 8. So everyone here has an octet, and all that's taken care of. So that's a good Lewis structure for NF3. I showed the steps already for CO2. So you saw that one. SeCl2. Go ahead and show you this one as well. This has, Se has 6 valence electrons. Chlorine has 7. And we've got 2 of them. So that gets us 20 electrons. Okay, remember the rule. Selenium, farther left. and chlorine outside atoms, single bonds to them, fill out the octets of those. And then double check. That's 2, 4, 6, 8. Another 8, 16. Wait a minute, we've got 4 electrons. Those go in the central. And now that's good. Everyone's got octets here and our electrons match up. So these are the steps. This is what you'll go through. You'll continue that with CCl4, H2CO, and you should come to some structure similar to this. You can see you're not going to be graded on how great does the drawing look, how wonderful. Does it represent 8 around here, 8 around here, 3 bonds? That's what we need. Okay. Carbon dioxide showed earlier how we had single bonds, and that meant carbon didn't have an octet, so we had to fold those electrons in. So that's the Lewis structure, a double bond to each oxygen, and then lone pair here. Drew the structure for this one. This carbon tetrachloride, that's 4 valence electrons for carbon, and that's 7 for each chlorine. So you can take a look, that should give us 32. And if we do this, that's 8 around each chlorine. So you could also draw it, I would draw it like this. Carbon tetrachloride, and everything has an octet. Each chlorine has 6 electrons for lone pairs there. Okay, so this last one, we got more atoms. Okay, so hydrogen has 1 valence electron each, so that's 2. Carbon we saw already has 4, and oxygen we saw has 6. So that's a total of 12 electrons. Okay, so if we do this, I'm going to put it up here because the structure will be coming in there later. Draw the terminal atoms. Remember, hydrogen only gets a duet. It's good to go. If we put lone pairs all around the oxygen, that has an octet. That's good to go. So here's a good question. That's 2, 4, 6, 8, 10, 12. 12 and 12 matches up. What's the golden rule of Lewis theory? Okay, remember that is about octets. So carbon does not have an octet here. So what we do is get rid of that lone pair. Not enough electrons to go around. We share. That's how we end up with this Lewis structure. So this is the process you'll go through. I encourage you to practice, homework, quizzes. This is what you'll be doing for Lewis structures. Couple of things. Again, exceptions. There's always exceptions. CHEM152Ch10, we go into great more detail about these exceptions, but I wanted to point out a few things. Lewis doesn't apply to everything, so some exceptions. Boron doesn't need 8. It's actually fine with 6. Beryllium's fine with 4, so it's a little different than the exceptions. Free radicals mean that you have a single electron, not electrons paired, so that's an odd number. So that's definitely different. You can't get octets. So like NO has an odd number. That's 5, 6. That's 11 valence electrons. So that's an odd number. You can't have pairs for everything. And then expanded valence. We talked about 3D and electron configuration. This allows for it to expand beyond an octet. So that's another exception. So remember, we're going from shape, structure determines properties. So we got to get to the structure, and that's this Vesper theory. Okay, so it's very impressive. You can talk to those around you and tell them, I'm learning the valent shell electron pair repulsion theory. Sounds so impressive, and you're going to see the explanation is quite basic and quite straightforward, and it makes a lot of sense. It's really helpful to get to structures. So we talked all about electrons, chapter 9, so we can't forget electrons are negative. Okay, I know we're drawing single bonds, we're drawing double bonds, triple bonds, we're drawing lone pairs. Those are still negatively charged. They want to repel each other. They want to get as far away from each other as possible. So if we think about this, we need a little geometry. Okay, So if we go up here, we got a circle. How many degrees are in a circle? Okay, good, that's 360. And if we think about things getting as far away from each other as possible on a circle, so we've got a central atom and it's connected to two outside atoms. It wants to get as far away from each other. That's 180 degrees. Okay, and we can continue going here in threes, that's 120, and fours, that's 90. So this is a geometry lesson to help get us ready for this structure. Okay, so the first structure is a linear geometry. That's carbon dioxide. You see how it says 2 electron groups? Even though those are double bonds, that's a 1 electron group. This is 1 electron group. They're in a circle, far away from each other as possible. That's 180 degrees. Now, we drew this molecule earlier, formaldehyde. It's got 1, 2, 3 electron regions. So 3 electron groups in a circle, divide by 3. That's 120. This is approximately because of the double bond versus single bond, but the main thing is that's separated 3 sections. I've got model kits, so if you want to come to office hours, we can look at these models, look at the 3D structure, see what it looks like. These first two, linear, trigonal planar, that's not too hard to see, but this next one for sure. What does a tetrahedral look like, okay? So remember when I drew a pie, a circle, and you split it in 4, that was only 90 degrees, okay? If you go to 3-dimensional now, a tetrahedral has a separation of 109.5. So electrons would prefer that because they want to get as far away from each other as possible. So you see this 2D drawing as 90 degrees, Lewis structure. That's not the actual shape of the molecule. So we want to look at it and say, what does the molecule look like? So those are the basic shapes. We had linear, trigonal planar, tetrahedral. Okay, so there are some other shapes, and that's based on when we have lone pairs. Okay, so this is a tetrahedral based shapes that we're going to talk about. So when we replace the bonds with lone pairs, it keeps the electron region, but the molecule shape looks different. So we'll take a look here at how to distinguish that. First, we can talk about the geometry of the electrons. Okay, the electron regions, how far away from each other are they? What is the shape? Okay, so that's the electron geometry. The molecular geometry, however, just wants to talk about the atoms. What are the shapes of the atoms? Okay, so if we take a look here, we can see that's 1, 2, 3, 4 electron regions. One of those regions is a lone pair. Okay, so the electron geometry is tetrahedral. That's the one we talked about with 4 electron regions. The molecular geometry, though, okay, that is just the molecule. That is, what is the shapes of just these atoms? Because there's a lone pair, it bends it down, and now that takes a different shape. So we want to know the molecular geometry shape. So what you can see is, what you'll actually see, this is gone. You can't see the electrons, but you can, when you study these, you can see the atoms, and it looks like this trigonal pyramidal. So the little wooden massage tool maybe you've seen before, that's got an atom above and 3 below in a trigonal pyramid structure. Okay, so that was 4 electron regions. The lone pair's gone, or the lone pair here we're not looking at, we're just looking at the molecule. Water, look at that. It has 1, 2, 3, 4 electron regions. 2 of those are lone pairs, so the electron geometry, we say, is tetrahedral. And now this is going to give us a different shape than before. So that we're taking out of our view, this we're taking out of our view. We're just looking at this. And remember, when we draw water like this, that is a Lewis structure, that is a 2D. We're talking now a 3D, and it's going to be bent. So now you can imagine it would be better to draw water like this, because those lone pairs force it into this shape. It's called the bent geometry. Again, we can look at that in office hours. I can show you how all 4 of the electron geometries have a tetrahedral shape. If you've got a lone pair here, a lone pair here, these stay in the bent arrangement. So the shapes that we're learning, if you take a look here, we saw 2 electron groups, so that was linear, and they're going to have bonds, they're going to not have any lone pairs. That's the linear molecular geometry, linear electron geometry. Okay, we didn't look at this one, but the 3 electron group also can have lone pairs. So if you take a look, 3 electron group, 3 bonding group, that's trigonal planar, different angles, 120 versus 180. If we have 1 lone pair in trigonal planar, it takes up 1 spot, angles are about the same, and that's also can be a bent. And then these are the ones we focused on, the tetrahedral electron geometry, no lone pairs, 1 lone pair, 2 lone pairs. That's tetrahedral, trigonal pyramidal, and bent. So these are the shapes that we'll talk about. You go to Chem 200, we'll add more shapes to this, but this is a great start. What do molecules look like? These are the shapes. So now you're going to be, and whether it's in lab or lecture, drawing these shapes, and it might help to have some of this 3D skills down, okay? So if it's in the line of the paper, you don't have to do anything. That's linear, that's trigonal planar, but look at this tetrahedral. You can draw a wedge. That's showing you that that's coming out towards you right now, okay? This is showing that's going behind you, so that is a better arrangement. For sure, that's a better arrangement than this. Remember, this shows 90 degrees. That's not what it is. It's tetrahedral 109.5. And these are some of the structures that come on in Chem 200. So wedged and hashed lines you can use. So go ahead now, draw the Lewis structures, H2S, BF3, and NF3, and the terminology, remember, what's the electron geometry, and then also what's the molecular geometry. So identify both of those. So if you take a look here, H2S, you have to draw a good Lewis structure, which means sulfur is the central atom, and it has 2 lone pairs. That means sulfur has 4 electron regions, so the electron geometry is tetrahedral. But it also has 2 lone pairs. That gives us this bent. So what's the shape of the molecule? It's bent. Okay, so we have to be clear what's being asked. Is it the electron geometry or the molecular geometry? BF3 we said is one of those exceptions, so it does not have an octet in this structure, but that is okay with boron. Fluorines all have octets. So you can see the central atom has 3 electron regions. That's trigonal planar. There are no lone pairs on that, so that means that has an trigonal planar electron geometry and a trigonal planar molecular geometry. And lastly, NF3, I want to point out here, BF3, NF3, they look similar, but look, they are completely different geometry-wise. That's because you have to have the Lewis structure, and the Lewis structures are different. Okay, so you have to have the steps, how to draw good Lewis structures, and then you have to be able to identify electron regions. Okay, so I've got here the Lewis structure, and you can see the central atom has 3 electron regions here, trigonal planar. The central atom here has 4 electron regions, that's tetrahedral. One of those is a lone pair, so the molecular geometry is trigonal pyramidal. So we've been drawing, we've been showing sharing of electrons. Of course, they don't all share equally. I mentioned this earlier. So some, I say, are more selfish than others. They pull electrons to themselves more than sharing equally. A level of selfishness or a measurement of this is electronegativity. How much will an element pull electrons in a bond to itself. Okay, so this is, we're going to see another periodic trend we saw before: size, metallic character, ionization energy. This will be another one, electronegativity, that we can look at the periodic table and estimate. So if we take a look here, what does this mean, electronegativity? Well, oxygen is more electronegative than hydrogen. So if we take a look here, you can see there's a little bit of electron region down here, but there's a lot of electron region over here. Okay, and we use these symbols. This is lowercase delta to say that's partial positive. That's partial negative. Okay, remember when we talked about metals and nonmetals, we had full charges. Okay, full positive, full negative. So we're just saying they're sharing unequally, and there's a partial positive, partial negative, and that's called a dipole moment. We have a pole, and you could also see this with an arrow, so a positive end of an arrow, and the negative, or the arrow end just pointing to the negative area where the electrons are more likely to be. So that's this representing this dipole moment. So that's the unequal sharing and what's called a partial charge separation. So if you have a covalent bond that's not sharing evenly, you can have polar covalent bonds. Okay, so one has more of the electron regions than the other, and the bigger the difference in electronegativity, the greater the polarity. Okay, so the trend in electronegativity is if you go to the right, it increases, and if you go up, it increases. And a good way to remember this is fluorine is the most electronegative. Okay, so it's assigned a value of 4.0. It's the most electronegative. Everything else goes up there, which makes sense, right? Because nonmetals want to give up their electrons, so they're not going to be electronegative. Nonmetals are definitely going to be the more electronegative. So these values you won't have to memorize. They'll be provided to you if you need to do a calculation, or you can just say the trend, fluorine is more electronegative than carbon. So if you take a look here, now we have a way to distinguish between bonds. Okay, we said ionic is a full transfer. Now we're seeing this terminology, pure or nonpolar covalent is when they share equally or pretty equally. And now what we've been talking about, these polar bonds, are unequal sharing. So what we're going to do is calculate the difference in electronegativity. So that just means if you have a bond between carbon and hydrogen, you look up the electronegativity, and carbon's 2.5 and hydrogen's 2.1, and you calculate the difference. So 2.5 minus 2.1, that equals 0.4. So if you calculate 0.4, then you look down here, it's right on the verge. Okay, so in this case, this actually is treated as a nonpolar bond. Okay, so carbon-hydrogen bond is a nonpolar or pure covalent bond. If we had carbon and oxygen on the other hand, that's 2.5, that's 3.5, this is a difference in 1.0. So then you can see 1.0 falls in here. This is a polar bond, this is a nonpolar bond. This is how we're going to use electronegativity. So I encourage you do a calculation or take a look at these questions and determine, is it pure or nonpolar, is it polar, or is it ionic? Right away, red flag should be these are the same. Okay, that means they're going to cancel out when you calculate the difference in electronegativity. So that's a pure covalent or nonpolar bond. Cesium and bromide, you can look and think right away, that's actually a metal and a nonmetal. You do the calculation, has a difference of 2.1, that's going to be an ionic bond. And then if you take a look, phosphorus and oxygen, do the calculation at 1.4, that would be a polar covalent bond. So what we're talking about right now are the bonds. Okay, really want to emphasize, you can have a polar and nonpolar and ionic bond. Well, now we also want to know about the polarity of molecules. Okay, so just because a molecule has polar bonds, that does not mean that it's a polar molecule. Okay, so we really want to emphasize the difference, bonds versus molecule. It depends on where these polar bonds are pulling. That's what we need to look at to figure out. So if you take a look, carbon dioxide, we already mentioned carbon-oxygen is a polar bond. This is a polar bond, but look, they're pulling the same strength in opposite directions. Cancels out, that's a nonpolar molecule. If we look here, these are polar bonds, nitrogen and fluorine. There is nothing pulling in this direction to cancel. So that is a polar molecule. So this chapter concludes with going from knowing about electrons in electron configurations to now moving to what do these molecules look like, what are their shapes. So there's a lot of things you can practice in here. Come see me in office hours if you want to go over this.